Have you ever wondered where cars go when they are no longer useful? Today we will explore the recycling process of old cars, new cars, and even luxury brands like Lamborghini, Porsche, and much more. Don't forget to like and subscribe. Let's go!
Phase 1. Reception, registration, and evaluation. When a vehicle reaches the end of its useful life, the recycling process begins in the reception area of the plant. There, its identification number, engine data, year of manufacture, and overall condition are recorded. Everything is integrated into a digital system that allows each unit to be tracked throughout the entire process. Afterward, a detailed technical inspection is carried out. Specialists evaluate which components can be reused directly: engine, transmission, alternator, starter system, electronic modules, multimedia systems, doors, seats, and other elements in good condition. These parts are carefully dismantled, tested, and sent to the used spare parts market. This stage is crucial because it maximizes the recoverable value before the vehicle is reduced to raw materials. The proper management makes it possible to separate reusable elements from those that will be processed as recyclable material, optimizing resources and reducing waste. Phase 2. Decontamination and fluid extraction. Once classified, the vehicle moves to the decontamination area. The first step is removing the battery. In internal combustion vehicles, the lead-acid battery is extracted, whose components, lead, plastic, and electrolyte, can be recycled almost entirely. In hybrid or electric vehicles, lithium-ion batteries are dismantled under strict protocols and sent to specialized facilities. Next, the complete extraction of fluids takes place. The car is placed on a platform equipped with hydraulic securing systems, using probes and high-pressure vacuum pumps. Fuel, engine oil, transmission fluid, coolant, brake fluid, and gas from the air conditioning system are drained. This procedure is carried out in a closed circuit with safety valves and pressure sensors that prevent spills or emissions. The recovered fluids are filtered and, when possible, reused as an internal energy source for plant machinery. This eliminates fire or contamination risks and prepares the vehicle for structural dismantling. Phase 3. Component dismantling and material separation. With the vehicle already decontaminated, systematic dismantling begins. First, the wheels are removed. Tires are separated from the rims. The rubber is shredded to obtain granulate used for modified asphalt, sports surfaces, or industrial alternative fuel. Steel or aluminum rims are sent directly to foundries. Next, windshields and windows are removed. Laminated glass, composed of layers bonded with polymers such as PVB, is processed to recover both the glass and the intermediate material, which can be reused in industrial applications. Doors are dismantled and their materials separated. Metal structures, electric motors, locking systems, wiring, and plastic components. Inside the vehicle, seats, panels, carpets, and the dashboard are removed and classified. Wiring is processed to recover copper, while plastics are shredded and prepared for mechanical or energy recycling. Engines and transmissions, due to their high value, receive special treatment. They may be refurbished for resale or dismantled to extract aluminum, steel, and valuable metals. This methodical phase ensures that each material follows the most appropriate recycling path. Phase 4. Structural pretreatment and compaction. After removing reusable parts, fluids, and the most evident non-metallic components, the vehicle body enters a key stage known as structural pretreatment. At this point, the objective is to prepare the structure for its large-scale transformation into raw material by eliminating any element that might interfere with subsequent processes. The body is transferred to an area equipped with high-power machinery. Articulated mechanical arms fitted with hydraulic shears and industrial clamps operate on the remaining structure. With precise and controlled movements, they remove exhaust systems, radiators, loose reinforcements, large plastic panels, and remaining wiring that may not have been extracted previously. These tools can exert forces of several tens of tons, allowing materials to be cut and separated in a matter of seconds. This stage functions as a preliminary filtering process. By removing heterogeneous or potentially problematic components, the compaction and shredding machinery is protected, and the quality of the material to be recycled is improved. Once pretreatment is complete, the body is reduced to a clean structure composed mainly of steel and, to a lesser extent, aluminum. Next, the shell is introduced into a high-capacity hydraulic press. These presses are designed to apply forces exceeding 150 tons, compressing the structure with enormous pressure. In just a few minutes, the original volume of the vehicle is drastically reduced, becoming a compact block that is much easier to handle. Depending on the type of installation, the body may be transformed into dense, stackable cubes, flat plates of reduced thickness, or cut sections ready for the next shredding phase. This reduction in size not only optimizes storage space, but also facilitates internal and external transportation and improves the energy efficiency of later processes. In this way, the vehicle structure is prepared for its final transformation into recycled raw material. Phase 5. Shredding and classification. In this phase, the previously compacted body blocks enter a high-capacity industrial shredder, considered the core of the metal recovery process. These machines are designed to operate continuously and withstand extreme loads. Inside, large shafts equipped with hardened steel teeth rotate in opposite directions, trapping the material and fragmenting it with enormous force. Within seconds, what was once a compact structure becomes thousands of fragments of different sizes. The result is not only shredded steel, but a complex mixture that includes ferrous and non-ferrous metals, along with light residues such as plastics, foams, and textile remnants that may still remain attached. Once shredded, the material moves along an automated separation line. The first step is usually carried out using powerful electromagnets suspended above conveyor belts. These magnets attract and separate ferrous steel from the rest of the mixture, ensuring efficient recovery of the main material. Afterward, the remaining flow passes through induced current systems, also known as eddy current separators. These machines generate variable magnetic fields that repel non-ferrous metals such as aluminum and copper, allowing them to be classified independently without direct contact. In additional stages, pneumatic systems and vibrating screens help remove lighter fractions. Plastics, foams, and textile residues are diverted to specific recycling or energy recovery processes. In this way, each component finds its appropriate treatment channel. At the end of classification, the recovered steel is compacted again into dense bundles ready for melting. Aluminum and copper are sent to specialized foundries, where they will be transformed into new alloys. Within a relatively short time, a complete vehicle can be reduced to organized raw materials ready to re-enter the production cycle, demonstrating the efficiency and precision of this key stage in automotive recycling. Phase 6. Melting in an electric arc furnace. At this stage, the steel recovered after shredding and classification becomes liquid raw material ready to begin a new industrial cycle. The previously compacted and cleaned metal fragments are loaded into electric arc furnaces, one of the most efficient and widely used technologies for recycling steel on a large scale. Inside the furnace, massive graphite electrodes descend from the top and generate extremely intense electric arcs. These arcs produce temperatures exceeding 1,600 degrees Celsius, enough to completely melt the scrap within minutes. The process is precisely controlled to ensure homogeneous and safe melting, optimizing both energy consumption and the quality of the final result. As the metal melts, impurities present, such as non-metallic residues or unwanted chemical elements, rise to the surface, forming a layer of slag. This slag is removed in a controlled manner, allowing the purification of the molten metal bath. At the same time, pressurized oxygen is injected to oxidize and eliminate components that could affect the steel's properties, such as excess carbon or other out-of-specification alloys. Throughout the process, advanced monitoring systems supervise the chemical composition in real time. Spectrometric analysis equipment takes samples of the molten metal and verifies the exact proportion of each element. If necessary, small quantities of ferroalloys are added to adjust the final formula and meet the technical standards required by the industry. Once the appropriate composition is achieved, the liquid steel is poured into ladles and transported to the continuous casting line. There, the molten metal flows into water-cooled molds that rapidly cool the outer layer, initiating controlled solidification. While the surface hardens, the interior remains partially liquid, allowing the steel to be molded continuously and uniformly. Along the path, rollers guide the material, while it completes its progressive solidification. Depending on the configuration, the steel takes the form of billets, slabs, or semi-finished bars, which will serve as the base for subsequent rolling and transformation processes. In this way, the recycled steel leaves behind its fragmented form and becomes a structured product once again, ready to acquire new dimensions and industrial applications. Phase 7. Rolling, cooling, and final inspection. At this stage, the recycled steel that has been melted and cast into semi-finished forms, such as billets, slabs, or blooms, is prepared to acquire its final dimensions and properties. First, it passes through reheating furnaces, where its temperature is raised again to optimal levels for controlled plastic deformation. This uniform heating is essential to avoid internal stresses and ensure homogeneous transformation in the next phase. Once the appropriate temperature is reached, the material enters the hot rolling mills. There, a series of large, high-strength rollers rotate in synchronization, progressively compressing and stretching the steel. With each pass between the rollers, the thickness decreases and the length increases, transforming robust blocks into thin sheets, continuous coils, or specific structural profiles. This process not only defines the final shape, but also influences the metal's microstructure, improving certain mechanical properties depending on its intended use. Throughout the rolling process, control is fully automated. Laser sensors measure thickness with millimeter precision, while high-speed cameras monitor alignment and detect any deviation in real time. Computer systems adjust roller pressure and feed speed to maintain constant parameters. This combination of industrial force and digital control makes it possible to achieve extremely demanding quality standards. After shaping, the steel remains at high temperatures and must therefore be cooled carefully. Cooling is not performed abruptly, as this could generate internal stresses or structural alterations. Instead, pressurized water nozzles create a controlled mist over the metal surface, gradually reducing its temperature. Later, industrial fans complete the process until stable conditions are reached. This thermal control ensures that the steel retains the strength, ductility, and dimensional stability required. Once the thermal stage is completed, final inspection begins. Each batch undergoes exhaustive controls. Ultrasonic equipment penetrates the material to identify possible internal cracks or unwanted inclusions. High-resolution cameras analyze the surface for irregularities, marks, or visible defects. In addition, mechanical tests are carried out to verify tensile strength, elasticity, and behavior under load. Only steel that meets all established criteria is approved. Once validated, it is marked with identification codes, registered in traceability systems, and stored as a finished product. From that moment on, it is ready to be integrated again into the industrial chain, whether in construction projects, infrastructure, machinery manufacturing, or even in the production of new vehicles, thus completing the full recycling cycle.
What did you think about this process? Let me know in the comments. Don't forget to like and subscribe.